Maybe. Maybe not. No. So we looked at the tensor notations, why tensors are useful, how to write down simple dot product, divergence, and so on in tensor notation. We looked at the Kronecker delta, the alternating set tensors that we're going to use today, examples of things that we're going to use, the nabla operator. I guess you'll know the nabla operator. Okay. So when you use the nabla operator on a scalar, it generates a vector. For example, on pressure. Okay, pressure is a scalar, and it generates a vector. So graph P, the gradient of P, so any pressure gradient. Okay, so this is just a gradient. Okay, gradient of a scalar, for example, pressure. The divergence of a vector, for example, your vector velocity, is simply going to be this in tensor notation, right? And you can generalize the gradient of a scalar and the divergence of a vector as a divergence of a second order tensor. So for example, you have a stress at the surface with all its 9 components, okay? And this is going to be the divergence of our second order tensor, okay? This is how we're going to write it. Skip this. So a nice exercise that you could do is to prove that the divergence of the curl of any vector field is equal to 0. Okay, just by using the divergence theorem. So use divergence theorem prove the divergence of the curl is equal to 0. You can do it very formally mathematically, or you can do it in a more physical way using an example of a control volume. Okay, just try it. We're going to do it in class next time. It's just a nice application of using the divergence theorem and the divergence of the curl in tensor notation. So the two theorems that you mentioned the last time, two theorems that we're going to use all year round in all classes. Stokes theorem, it relates a surface integral, okay, so the integral over a surface, to a line integral. So, an example, take a bell-shaped volume, okay? So this is going to be my area, which is bounded by a line, a bounding curve, where the area is open, okay? So I have a line C, a bounding curve C, and this is my dA and dA. Okay, so the surface has a magnitude, dA, and an orientation, and the normal vector. So this is my dr over the bounding curve. So what does the Stokes theorem say? Stokes theorem say that the surface integral of the divergence, sorry, the curl of the vector field is equal to the line integral around the curve that is bounding the surface. Okay? So this is a very useful theorem, or for any manifold omega, you can write okay, so you have a vector field, you integrate it over this area, imagine a bell, okay? So the curl of that vector field integrated over the area is equal to the line integral of the same vector field around the bounding curve. We'll see an example of why this is extremely useful. Okay, so that's the Stokes theorem, and the Gauss theorem, we've seen it the last time. Okay, this is even more intuitive. You have a volume, closed volume. Again, you have a dA, and so in this case the Stokes theorem says that the volume integral of the divergence integrated over the whole volume. Okay, you have, for example, velocity, it could be anything, any vector. Okay, the divergence of the vector field integrated over the volume is equal to the integral over the area bounding the volume of that vector field. Okay, this is even more useful in fluid dynamics. So basically, you have a control volume that we're going to use to derive all the conservation laws. So you consider a control volume of your fluid, and the divergence of your property within the fluid, within the volume, sorry, the divergence of your fluid within the volume is going to be equal to the area integral bounding the volume of the same vector field. Okay, so for example, if you have sources and sinks of velocity or any other tracer that you might consider, okay, inside your volume, the net sources and sinks will be equal to the area integral of your velocity. Okay, so you've got stuff going in and out. The net effect will be the outward flux of your vector field. Okay, that's intuitive. Okay. You decide to take your atmosphere or your ocean or your solid earth fluid. Okay, you decide where to integrate your fluid within a certain volume. You look at all the sources and sinks. So the divergence, sources minus sinks, is going to be equal to the flux of your velocity or tracer out of the surface bounding the volume. Okay, so you'll get this note. So this is the Gauss theorem, or called the divergence theorem, if you have a vector, okay, and you can write that in tensor notation that way. Okay, and the Stokes theorem is just this. Okay, the area integral of the curl of your vector field is equal to the circulation around the bounding curve of your vector field. Okay, so now we can start with the kinematics, which is a little bit more fun. Okay, so as I said, basically we're going to cover three main topics. One was statics, which we looked at, the hydrostasy in static condition, deriving the hydrostatic balance, why hydrostatic balance is interesting, in which conditions. And then we looked at the some recap of the tensors and a couple of theorems that we're going to use. And then we're going to look at the kinematics and the proper dynamics of the fluids. Okay? So kinematics is just describing the fluid and its movement. Okay? It doesn't explain why the fluid is moving, it's just describing the fluid. And we're going to do that through streamlines, trajectories, describing the vorticity of the fluid and the deformation of the fluid particle. Okay? You have a fluid particle which is subject to some force, we still don't know which one, and the fluid particle will be deformed, will be advected, will be accelerated, okay? Might rotate and acquire some vorticity. So we're going to describe what is happening to that particle of fluid through kinematics. Okay? But we still don't know why the fluid is moving. That is going to go into the dynamics. Okay? Dynamics then will study the forces acting on the fluid. And we're going to write down all the equation of motions. So on one side you'll have the kinematics, and on the other side you'll have the forces acting on the particle of fluid. Okay, so you can describe the motion of a fluid in two ways. One is the Lagrangian way, and the other way is the Eulerian. Okay, so the Lagrangian description of a motion is essentially following an individual particle. Okay, so you have one particle at one time, and you follow that particle in time. Okay, so this is, for example, what the Argo float is doing. Okay, if you remember that big thing, okay, that big thing is moving with the flow and is describing Lagrangially the fluid flow. Okay, so an instrument is moving with the flow and is telling you the velocity vector at all times, following one particle. Okay, so it's saying Lagrangially you're describing the movement of this particle, and you're saying this particle is changing in time in this way, and it's going in this direction with this velocity, with this vorticity, or whatever. Okay, so you're describing Lagrangially the changes in that particle. So you're following the particle. Whereas Eulerian description, one focuses on what happens in a special point. Okay, so as opposed to the Argo float that follows the flow, you are fixed in one position, so you're fixed here. Okay, and the fluid passes through your instrument or your frame of reference. Okay, and so you're saying at this point, at this location, the fluid today, at this point, at this time, has this particular velocity, this particular deformation, this particular vorticity. Okay, you don't know what is happening here, if this is space. If this is space, okay, you don't know what is happening here, and you don't know what is happening there. You just know what is happening at this location in time. Okay. So you don't know what is going to happen to the particle afterwards at different locations. You just know that this particle of fluid had these characteristics at this location, and after some time delta t, the particle of fluid passing by this space will have different characteristics. So you're not following the particle, you're just describing in an Eulerian framework what is happening to the flow at this particular location. Okay? But there's a way of combining the two, and to combine the two is describing the fluid flow, which is subject to changes in space and changes in time. Okay, so basically you have a fluid flow with changes in space, and its characteristics are changing also in time. So how can you combine the two is through the Lagrangian derivative, which is what we use to describe all our flows kinematically, and then we study the forces acting on that fluid. So this is the Lagrangian derivative. Engineers call this the material derivative. Okay, same thing. Okay, so you have your frame of reference, x, y, and z, and you have a variable f, which could be, a scalar or active, and you want to calculate the rate of change of this variable, okay? Because remember, in fluids, we're not interested in the change of a variable, but we're interested in the rate of change, okay? The d by dt of the changes in this variable. So we have an f here, which is a function of space and time. Okay, and after some delta t, this particle will be here. Okay, so changes in space after some delta t. Here, something like that. Okay, so there will be a increment in dz, in dx, and in dy. Okay, so how can you describe what has happened to this variable f that has changed in space and time? So if you remember, we used Taylor series before. So we're going to do Taylor series of your some a plus delta, whatever. And that is simply going to be whatever, or your Taylor series. So if we do that to our function f, which is well, x, for example, in the x direction. Okay, we can just truncate it that way. And we did that when we were looking at an infinitesimal, to a volume of fluid, and we looked at the balance in the vertical when we added weight. And then so the balance in the vertical within the pressure gradient and the weight giving rise to the hydrostatic balance. Right? So if we do the same, so what is the rate of change of f in all the directions? If we do it in x, so you have okay, so just the rate of change of f, here and here, and that is simply going to be equal to this, okay, so just the increments in x and y and z, and time. So we can write this as the increment, so the changes in f are equal to the changes in time plus the changes in space. Okay? So what is the rate of change of f is given by the changes in time and the changes in space. Now you can relate dt and dx. Through the velocity, of course. So now you can write d by dt of f is this plus this, right? Because I've just substituted dx by u dt. Okay, so the rate of change of f is given by d by dt of f plus the changes in space of f times the velocity vector. So this is the advection coefficient. So there is a flow that is advecting my f, my variable, and f changes in time. Okay? So if it's a wave, the wave changes in time, it's time dependent, and there might be some interaction with the background flow, u. Okay? So there is a background flow and there is a wave that you want to describe. That wave will change in time and in space, and this is the advection coefficient. Okay? Advection. Sometimes your variable doesn't change in time, so df by dt is equal to 0. Okay? We're going to do that assumption in GFD a lot. Okay? If you're not talking about waves, you can just neglect the d by dt, and so you're left with the advection term, or for example, u, d by dx of u times u, the advection, equal to some forces. Okay, and so you look at the acceleration of your velocity. Now, why are we doing this? You can write this as the rate of change of f is d by dt of f in tensor notation. And now we can define this d by dt as capital D. And this d by dt is called the Lagrangian derivative. Okay, so this is the Lagrangian derivative. The Lagrangian derivative means that you're both following the particle in space and you're looking at the changes in time. Okay, so it's a Eulerian. The framework is Eulerian, but you're actually Lagrangially describing the fluid flow. Okay? So this is what is called the Lagrangian derivative. And we're going to use Lagrangian derivative all the time in the equation of motion. Okay? So we're going to say that capital D by dt of the velocity is equal to the changes in time plus the advection equal to some forces. The pressure gradient, gravitational force, surface stresses at the surface or at the bottom. Okay, so you're describing all the changes of your fluid particle, all the accelerations of the fluid particle, which are going to be equal to all the forces that are generating those accelerations. Okay, so we're going to use, you're going to use d by dt a lot. So this is the Lagrangian derivative. So this is just for describing the fluid flow. We still don't know why the flow is accelerating or is acquiring vorticity or anything like that. We're just describing the characteristics of the fluid. Okay? So that's the Lagrangian derivative. The d by dt of f is the local rate of change of f. Okay? So in a fixed point, what is the local rate of change of my particle? That's the d by dt, the first term. Whereas the second term, the d by dx, is the advective derivative. Okay, so it's the change in f as the result of advection of the particles from one location to the other. The particle has moved from one location to the other, and that was because of some advection process by the background flow. Okay? So you're both, in an Eulerian way, looking at the change in time of your characteristics, and you're also following Lagrangially the fluid particle. Okay? So the Lagrangian derivative is is doing both. So how can you describe the, if you don't have one particle but you have many particles and you want to describe the whole flow, then you use streamlines. Okay, so if you want to describe all the particles in your flow, you do that through the streamlines. So imagine that you have a flow and you have a velocity vector, and at any point you have some velocity vector which is a function of time. Okay, it could be fixed in time actually, but generally it's a function of time. So you can describe streamlines of the flow. So we do again graph. You have a velocity. Not very good at drawing. You have a velocity vector u. Okay. And you have a ds, which is an element of the arc length of the velocity vector. So that ds is equal to dx, dy, and okay. So this is just an element of the arc length of your velocity vector, and this is the trajectory that your velocity vector is following. So how can you build your streamline? You have a v component and a u component of your velocity vector, and here you have a dy and a dx. Okay, so basically you want to trace your velocity vector in time, and when you trace your velocity vector in time, you will build a streamline. Okay, that will follow Lagrangian the path of your particle, and those streamlines will see that they might change in time. If the velocity vector changes in time, those streamlines will change, or they might be fixed if the velocity vector doesn't change in time. Okay, so the this is tangent to the velocity vector, of course, okay, because it's an element of the arc length, so that's tangent. So by definition, you have that the velocity vector is parallel to the element of the arc length. So those two are parallel. Therefore, this is equal to 0. Okay, because they're parallel. So if you do this, ijk of your velocity vector, dx, dy, and dz, you will have v dz minus omega dy y plus omega dx minus u dz dj plus u dy minus v dx in k. Okay, and this has to be 0, and it has to be 0 for all of them, because you can reduce the problem to two-dimensional or one-dimensional. So you can substitute that, and you will have that v dy is equal to omega dz, and omega w dz is equal to u dx, and u dx is v dy. Okay, because each of those have to be equal to 0. So u dx equal to v dy equal to w dz. And this is true along any of those curves which are streamlines. Okay, so by definition, this element of the arc length ds is parallel to the velocity vector u, and if they're parallel, the wedge product is equal to 0. And this is true for every direction, because you could reduce this to a two-dimensional or a one-dimensional problem. Okay? So all of these have to be equal to 0. So H1 will give you this. Or you can rearrange to give this. And this is true along the streamline. So at any point, you can build a velocity vector with an element of the arc length, which is parallel. Okay? So this gives you the coordinates of the streamline. So for a two-dimensional flow, or a 2D flow, what do you have? You have dy of dx is equal to v over u. Okay? So the slope dy over dx, the slope of the streamline is equal to the tangent of the angle. Slope is equal to tangent of the angle formed by the velocity vector. Okay? So if you know the vector field, if you know the vector field, u, then you can build your slope dy by dx, and at any point and any time t, you can build the coordinate for your streamline. Okay? So you can build your streamline. As long as you know your velocity vector, you know the coordinates for the streamline. Okay? And this is what happens if you know your velocity field. Could be a wind field, or it could be an ocean current, or it could be a fluid inside of the Earth. Any fluid, okay? You know the velocity vector, u, in space, which is a function of space and time. And just by the velocity vector, you can build the streamline at any point and in time. Okay? So if you remember that black object, which was the rock or whatever, okay? At any point in space, you know the velocity vector, and you can build the streamline of the flow. Okay, so these black lines are the streamlines of the flow. Okay, so that is telling you at every point the direction of the flow. Okay, the streamline is parallel to the flow, so this gives you the direction of the flow. And if the flow gets unstable, here is laminar, and here it gets turbulent and unstable because of the interaction with the element. Then we'll study instability problems in the second part of the course. Okay? You can use wind vectors and build your, if you see the gray, continents underneath, okay? So this is Europe, Africa, and the Americas. That is an instantaneous image of the wind vector, okay? You put together all your wind vectors, you compute the streamlines, and you get all these arrows. If you have a very good eyesight, you can see some arrows, little arrows, okay, that gives you the direction of the streamline. Okay. If an engineer, you can use streamlines to build better aerodynamics in your car. Okay, so that's what they do. Obviously, streamlines. So this could be a steady flow, which is not a function of time. Okay, so you build your streamlines, and your streamlines are not a function of time. So that would be valid for any time t. But most of the time, streamlines do change in time. Okay, so your velocity vector just does change in time, and so you have to compute your streamlines at any delta t. Okay, so those streamlines will change with time, and you have to compute your streamlines at every time. Okay, so some definitions and properties of streamlines. They're close to a solid boundary. Streamlines are parallel to that boundary because, by definition, they are parallel to the flow. Okay, the flow cannot go into the boundary, and so the flow will have to go around the boundary, and so the streamline. The direction of the streamline is the direction of the fluid velocity, because by definition it's parallel to the fluid vector. Fluid cannot cross streamlines, of course, because by definition they're parallel. Okay? So if one particle of fluid starts in this streamline, it will never go into the other streamline, okay? Because by definition, the fluid cannot cross the streamlines. Streamlines cannot cross each other for the same reason. Any particle starting on one streamline will stay on that same streamline, even though they change in time. In unsteady flow, streamlines can change position in time. Okay, so if the flow is steady, there is no d by dt. Your streamlines are fixed because the velocity vector is fixed in time. If the velocity vector changes in time, those streamlines will change. So obviously, this example of wind field is for one particular day. After a second, those streamlines will be different because the velocity vector is different. Okay, so differences between streamlines and path lines. Streamlines are a family of curves that are instantaneously tangent to the velocity vector of the flow. Okay, and this shows the direction of a fluid element traveling at any point in time. So this streamline will show the direction of the velocity vector at any point in time. Those are the streamlines. Path lines are the trajectories that any individual fluid particle follows, okay? And those are different from streamlines. So it's basically can be thought as a recording of the path of a fluid element in the flow over a certain period. The direction of the path takes will be determined by the streamlines of the fluid at any moment in time. So if the flow is steady, the streamlines are equal to the path line, okay? So if these are my streamlines and the flow doesn't change in time, if I follow a particle as this streamline and in space it will have this streamlines, okay? So this is the path line and this is my streamline, okay? So if the streamline, if the streamline is fixed in time, the streamline and the path line are the same. If you have this streamline now, okay? So this is my streamline, and this is my path line, and the two are the same. If the streamline changes in time, so at time t plus dt, my streamline now has changed and is something like this, okay? So the path line now is not the same as the streamline because the streamline has changed in time. So that's another example, okay? So you look at every different point in time, what is the trajectory of the fluid, okay? If the streamline is fixed, then the trajectory of the fluid is the same as the streamline. But if the streamlines are changing, the trajectory of one individual particle is not the same as the streamline anymore. Okay? But we're going to use streamlines anyway. Path lines are not very interesting. Path lines are interesting if in an Eulerian way. So if you're fixed, you know that the flow has this particular path line, okay? But the streamline might change in time. So if the streamline is fixed, the two are the same. If the streamline changes in time, then the streamline and the path line don't have to coincide.
So the streamline is just the line where all the velocity vectors are tangent.
Yes.
To which all the velocity vectors.
Yes. Not a single particle.
While the path line, yeah, it's the same, but for a fixed particle.
For a fixed particle. So a fixed particle at one particular point in time has one direction, which is the path line. But the streamline changes in time.
Yeah.
So the streamline is not the same as the path line at one particular time anymore, because they change. So if one is dependent on time and the other one is not dependent on time. So if the streamline is not dependent on time either, then the two coincide. Okay, but we use streamlines. So what is a stream tube now? So instead of thinking of a two-dimensional flow, now you're thinking of a three-dimensional flow. Think of a pipe. Okay. So all streamlines passing through a closed curve C, which is that red circle, for example, okay, they form a stream tube. So all those blue streamlines, they form a stream tube passing through a closed curve C. The walls of the stream tubes are streamlines. Okay, so all those streamlines are forming a stream tube passing through the closed curve C. And fluid cannot close the streamlines, and so the fluid cannot cross the stream tube surface either, because the stream tube surface is made of streamlines. Okay. And stream tube can change position in time if the streamlines do change in time. Okay. So when we do conservations over a volume, we can use streamlines, and that volume might change in time and could be advected, okay, if we follow a volume of fluid that is within a different fluid. Okay, we do our conservation inside of a particular volume. That particular volume can be thought of many streamlines forming a stream tube, and that stream tube can change in time. So we do all our volume integrations over that stream tube, and that stream tube can change in time. Okay. Okay, so this is just kinematics. So we're just trying to explain the characteristics of the fluid. So we saw the Lagrangian derivative that is trying to explain both Eulerianly and Lagrangianly the kinematics of the fluid. And then you can visualize the kinematics of the fluid through streamlines or stream tubes in many ways. Okay. We're not going to talk about forces yet. Okay. But we're just going to explain or characterize the deformations of a fluid particle. Okay. We still don't know what causes the deformation of this particle, but we can describe the deformations of this particle or fluid. Okay, so if you remember, you have a strain, for example, on a particle, and that particle will respond with a linear straight or a shear straight, and then we can put together all of them. So we're going to take a simple element of fluid, and we're going to study the deformation of this element of fluid, subject to some force. Okay, so there could be normal strain, okay, and there will be the change in length per unit length of a linear element. So you have an element, you have a normal strain, and that element changes its length linearly. Okay, so you have an element of fluid. Yes.
Excuse me. Just thinking out loud. You're saying streamlines do not cross. How then can you model, for example, if one river is moving this way and another river is crossing, at the instant when they are crossing, it becomes really messy. Like, how do you define the streamlines at that point? Like, the two are mixing.
Mixing is a different thing. So we're not talking about mixing yet. Okay. So you are defining at every point in space the direction of the fluid. Okay. So in this particular place, the fluid goes like this. Okay, and this is the direction of the fluid. The streamlines are parallel to the fluid flow, so this gives you the direction of the fluid. Then there is another fluid coming from here, okay, and it changes the direction of the fluid. Don't worry about mixing yet, okay, so it changes the direction of the fluid. So at time t plus dt, maybe this streamline is the same, this streamline is the same, second streamline is also the same, this streamline is now like this, okay, has been deformed by injection of some other fluid. So you're taking pictures and snapshots of the velocity vector, and you're putting together all the velocity vector in space. Okay, you have your velocity vector here, and here, okay, and you're putting together all these velocity vectors, and you're defining the direction of the flow through streamlines. This changes in time or maybe not. If you have two rivers merging, then these streamlines will change a lot. Okay? Because the direction of the fluid will change. The direction and the intensity of the flow will change a lot. Okay? So these streamlines will change a lot. If you have a laminar fluid, if you have a river like this, okay, this is the these are the walls of the river, and you have a laminar fluid like this. Okay, these are streamlines, and there's a flow going from left to right. Okay, and for example, this doesn't change with time. Okay, so this is my velocity vector, and these are the streamlines. If you have a very turbulent fluid, okay, at some point the streamlines are like this, for example, okay, and at t delta t, the velocity vector are going to be like this, the streamlines. Okay. So the streamlines will change a lot because there is a lot of changes in the velocity vector. So the streamlines is just putting together instantaneous direction of the velocity vector. The velocity vector can change in time and in space. Okay. So if the flow changes in time for any particular reason, the streamlines will change in time. If the velocity vector doesn't change in time, then the streamlines are always the same. Okay. You can describe the flow at any instant, and you will always get the same streamlines. So you have an element of fluid, and this element of fluid can change in two ways. One is through normal strains. Okay, so we're going to do an example. But you have an element of fluid. Okay, you have a normal strain, and this element of fluid might compress or expand because of this stress, which is normal. Okay, so this element of fluid might be enlarged or compressed because of this normal strain. If you have shear strain on an element of fluid, shear strain might deform the element of fluid. It's not normal anymore, it's a shear strain. Okay? So this element of fluid might deform with some angle. And so we're going to define the changes in this element of fluid through normal strains and shear strains. Okay? Again, we are fluids, and so we don't care about the final position, but we care about the rate of change. The rate of change in of the normal strain and the rate of change of the shear strains. So how the fluid deforms through a normal strain and through a shear strain. Okay. So we're going to do an example, and we're going to build some useful tensors that will describe all the deformation. Okay, so we're going to do first the linear strain rates, then the shear strain rates, and then we're going to put all of them together to define kinematically what happens to an element of fluid under linear and shear strains. Okay, so let's first talk about the linear strain rates, and let's make a simple example of an element of fluid, this, from some A to some B, and we have a velocity which is doing a linear normal strain to this element of fluid. This is some delta x1. Okay, and this is at time t, and at time t to delta t, we're going to have this element of fluid. The same element of fluid has now been deformed by this linear strain or normal strain. So now we have a prime and a b prime. So again, here I have a U1, here I have a U1 plus because of the length delta x1. Okay? So what is happening at t plus delta t? We have that now this is u1 dt, and this is u1 plus dt. Okay, has been deformed after some time dt. Okay. So now we can see that A prime B prime is equal to AB plus BB prime minus AA prime. Okay, so A prime B prime is equal to AB minus BB prime plus BB prime minus AA prime. So this is A prime B prime. So what is the rate of change, which is what is interesting? The rate of change per unit length. Okay, we don't care about the delta x1 per unit length. So what is the rate of change of this element of fluid per unit length? It's going to be material derivative. So the rate of change of delta x1 per unit length is equal to the rate of change A prime B prime minus AB over AB. Okay? The rate of change per unit time, so this is the rate of change per unit length, the rate of change. Other things that you want to remember, A prime is U1 dt, A prime is U1 dt, B prime is dt, and of course AB is delta x1. Okay, so now we're going to substitute all that in here. So this is the rate of change per unit length of A prime B prime, which is AB delta x1, plus B prime, which is dt. So that was A prime prime minus AA prime U1 dt minus AB delta x1. Okay, just substituting this with this. So now this goes away with this. This goes away with this. And we have per unit length minus the U1. Okay, and this goes away with this, and this goes away with this. So what are we left with? This. Okay, so the rate of change per unit length of my element is equal to the rate of change of U in X. Makes sense, right? And we have used the Lagrangian derivative. So we can generalize this to a volume. okay, for a volume. Yeah.
Excuse me, Professor. Why are you dropping the advection term from the Lagrangian derivative?
Why am I dropping?
The advection term? Because
No, I'm not dropping anything. The advection term is still here. The Lagrangian derivative is here. So the total change in the delta x, okay, the rate of change, I can express the rate of change as the rate of change of the changes in the x1. And the changes in x1 are a prime b prime minus the ab per unit length. I'm just expressing the same thing in a different way with this example. Okay? So I am doing, so the rate of change per unit length of my element is equal to, and in this simple example I'm substituting all this a, b, a prime, b prime with all this. Okay? So the rate of change per unit length of my element of fluid is going to be all this, simply this, opposite. So d by dt, the Lagrangian derivative per unit length of my element of fluid is equal to this. So the Lagrangian derivative is still here.
But from the definition, you say d by dt is equal to the rate of change, the partial derivative of d by dt plus ui d by d of x.
Still here. I'm not touching the Lagrangian derivative. I'm saying the rate of change, and then I can express the rate of change with the Lagrangian derivative for a full description in Eulerian and Lagrangian space. So the rate of change of my element of fluid per unit length is equal to, I can express the same thing, the rate of change in time per unit length of my simple case, okay, which is just simple two-dimensional, one-dimensional case. Okay. In a one-dimensional case, this is the rate of change per unit length, the rate of change per unit length of my one-dimensional element of fluid. Yeah, and with this simple example, I can substitute all this and get this. So the Lagrangian derivative is still here, is equal to, in this simple case, this. If I now use a volume, three-dimensional volume, okay, so the rate of change per unit volume is going to be equal to all the changes of u in the three dimensions.
May I write what is confusing me?
Yes?
You only have the term with correspondence to. This is another opportunity. What unit is defined by this column? It has the friction term. But from your description here, I don't see this term feature.
Is it there? But in one-dimensional problem, you can just describe it that way. But I'm not taking away any of the terms of the Lagrangian description. I'm just doing a simple one-dimensional problem. Okay. And so I'm saying I could have started with, so the rate of change of my element of fluid per unit length is equal to, let's go to a simple one-dimensional problem, the rate of change of the element, which is this way because you can describe the changes through the d by dt plus the advection, but I'm not touching that yet. Okay, so the element of fluid, the rate of change in the element of fluid, which you can describe in many ways, per unit length, are going to be equal to something. Okay, and in this simple problem, I'm just looking at this simple one-dimensional geometrical problem, and you say, well, this element has gone from AB to A prime B prime. I'm not saying how, the d by dt plus the vector. I'm just saying that it went from AB to A prime B prime. So I can just say whatever happened to this, in this simple case, the final result is A prime B prime minus the original AB per unit length, the rate of change. But I'm still not describing how it happened. That's the Lagrangian derivative. Okay. So in this simple case, I can say, okay, so the Lagrangian derivative, which is the rate of change that I'm interested in, is, in this simple case, A prime B prime minus AB per unit length, the rate of change. And I'm just substituting those with a simple example, and I'm getting to this. Yep. And you can generalize that with a volume, and it's this. Obviously, right? You can do all the three, in all the three dimensions. So the linear strain rate is just and now we can define a very useful tensor. Which is called the velocity gradient. The velocity gradient tensor. Okay, so in three-dimensional, the linear strain rates are given by this. So the element of fluid might deform this way, and in and out of the bond. Okay? And that will be described by the Lagrangian derivative, the two terms. Okay? But what I see is these three deformations, in x1, in x2, and in x3. Okay? And I can describe that through the Lagrangian derivative. So now I can define a velocity gradient tensor, which is this tensor, where I will have the diagonal terms are going to be my linear strain rates. You're still not convinced?
I'm confused. Especially now you go down here. You only capture the term with respect to xi.
So whatever happens, the rate of change per unit length, okay, will be given by this, and these are my linear strain rates. So it will deform in x1, it will deform in x2, and it will deform in x3. Okay? And that could be a rate of change. So for any delta t, I am deforming in x1, I am deforming in x2, and I'm deforming in x3. And these are going to be my linear strain rates. Linear in x1, linear in x2, and linear in x3.
Let me ask one. What makes the difference between first expression up there and the expression immediately down? Because there you're saying delta x1, and here you're saying delta v. But
So this is a simple one-dimensional problem. Okay, I'm just looking at u1. So deforming in x1. So I have a linear strain rate, okay, and I'm deforming in x1. Okay, just to make the simple example. And I got to this. So this is going to be my linear strain rate in x1. If I now consider a volume of fluid, I have x1, I have x2, and I have x3. Okay. So the rate of change of my volume, my particle, per unit volume is going to be to the deformations in x1, the deformations in x2, and the deformations in x3. So the element of fluid might deform like this, might deform like this, and it might deform like this, subject to linear strain rates. So the element is not deforming with a shear, but is deforming linearly in all three directions.
Problem.
We can talk later. Okay, so this is a very useful tensor. Okay, the velocity gradient tensor, where the diagonal terms are my linear strain rates. Okay, and the other terms they're not. So this is the linear strain rate, but then we can deform with a shear. Okay, so now we'll do again a simple example where now I have delta x1 and delta x2. Okay, I have a u2 in this direction. Here is u2 plus x1 x1. Here I have a u1, and here I have a u1 plus. Okay, and what is going to happen to this element of fluid is that it might be subject to a shear. Okay, so instead of just deforming in x1 or in x2 or in x3, this element of fluid might be subject to a shear and rotate. Okay, or get shrinked. Okay, or expand in this way. Okay, so now these two are not the same, so there is a shear. There is a shear in x2 or there is a shear in x1. Okay, so this might go like this and this might go like that. If these two are the same, there's just a linear strain rate in x1, for example. Okay, so if this is at time t, at time So let me draw this properly. So now the element of fluid was subject to a shear and it deformed. So this was A and this was B. Now I have B here and A here. Okay? So now I have my U1 is after some dt. This is this. Then my B now is U2 after some time t. And this is this U2 after some time t. And then this is U1 after some dt. Okay, so now there's not just a linear strain, but there is a shear strain. So these two got shrinked in this way because of the shear. So now I have formed two angles. I call this beta and I call this alpha. Okay, and that's the rotation that was acquired because of the shear. Now, the alpha is CA, the alpha is, where is C? The alpha is CA, CB. Okay, and if you substitute as U1 plus U1 dx2 delta x2 dt minus U1 dt over the CB, which is just delta x2. And this is this. Whereas the beta angle formed by this shear in the other direction is the same dt minus u2 dt over delta x1, which is u2 dx1 e dt. Okay, those are the two angles that I've generated because of this shear strain rate, of this shear strain. Okay. So now what we care is the rate. So the rate of shear is the sum of the two. Okay, so the shear is what caused these two angles. And so the rate of the shear, now the rate of the two angles caused by the strain rates acting on the element of fluid. And so this, if you substitute, is the rate of change and the dt. Okay, so the rate of change of the shear is now given by these two deformations, du1 by dx2 and the du2 by dx1. If there is no shear, there is no angle alpha and beta, and you don't have any shear, but you might have a linear strain. Okay? So if you do form angles because there is a shear in your strain rate, then you're causing this deformation. You can just generalize that way. Okay, so the linear strain rate, we said it was this. Any linear shear will cause you a linear strain rate in x1, in x2, or in x3. And the shear strain rates are going to be this. These are my shear strain rates. And now we can define an even more useful tensor. Can I erase this? To combine the two, which is a strain rate tensor. Okay, and the strain rate tensor will have both the linear strain rates and the shear strain rates. Some of this component might be zero if there's no shear or if there's no linear strain. Okay? But we can define this tensor E which is this. Okay? So this is going to be my strain rate tensor. So if you expand this, what are the diagonal terms? The linear strain rates. Right? So these are the linear strain rates. And the off-diagonal terms I'm just doing one example. And the off-diagonal terms are half the shear strain rates. Okay? So these two are the two halves of one shear stress, then this and this will be the other two halves of the other shear strain rates, and these two are going to be the other two halves of the shear strain rates. And these are the linear strain rates. Okay? So you have one tensor, E, which is giving you all the strain rates acting on the element of fluid. Okay, the linear strain rates and the shear strain rates in the three components. Okay, some of these terms might be zero. You don't have any linear strain rate in one direction, or you don't have any linear strain rate at all. Okay, so some of this component might be zero. But this tensor is encapsulating all the strain rates in the element of fluid. Can we just do one more thing?
No? Late for the ceremony.
Huh? What is it?
We are late for the ceremony.
Ceremony at 2:30.
Oh, you said.
Got plenty of time.
Oh, okay, good.
Good try.
Sorry, I'm sorry. I love
You only have 2 hours to go there. Now, I just want to do this because now that you have the linear strain rates and the shear strain rates in your head, hopefully, now you can understand what why the strain rates are useful. If you remember that element of fluid that got deformed, okay, because of shear, okay, it might deform in a particular way and acquire what is called vorticity. Okay, so if you have a shear rate, this element of fluid might start to rotate, and that is called vorticity. Okay, so the definition of the vorticity is through the rotation of this element of fluid. So if we go back to the same example, I'm just drawing some of this. Okay, that was the element of fluid that from this original position got deformed to this new position, and it formed two angles. Okay, from this it got deformed to this, and it formed two angles, alpha and beta. So now let's imagine that we have x1 here, x2 here, and x3 is out of the board. Okay, so we want to see how this element of fluid might be rotating around the axis x3. Okay, which is usually what we care about in geophysical fluids, is the rotation of an element of fluid around the vertical axis. Okay, that's the most important, usually the most important thing of an element of fluid. Okay, so the axis 3 is out of the board, and we want to see if this element of fluid is acquiring some rotation because of the shear strain rates. Okay, might not, start to rotate, but it might start to rotate. That was an excuse me? No. No. So we want to see the angular velocities. The angular velocities that this element of fluid is acquiring because of the shear strains. Okay, so we have two angular velocities. One is delta d by dt of beta. Okay, so there's an angular velocity around the axis 3. And there's another angular velocity, another component of the angular velocity, which is minus d alpha t. Okay, and the convention is that because x3 is coming out of the board, this delta b, in this case, this delta b is positive. Okay, you know the right-hand rule. Yeah. Okay. So in this convention and in this example, d beta is positive, is growing in this direction, and d alpha is negative around the axis 3. Okay. So the angular velocity that this element of fluid is acquiring has two components, d beta and minus d alpha. Okay. So you have to take into account both changes to get the rotation of the angular velocity. So you take the average of these two components of the angular velocity. Okay, and this is going to be on the around the third axis, axis 3. Okay. So that's the angular velocity that this element of fluid has probably acquired because of this shear strain rates. Okay? And now the definition of vorticity is that vorticity omega, it's not W, okay, omega, is twice the rotation rate. Okay, so that is the definition of vorticity. So now we can look at the, and we can prove this in a very simple way. Okay? So vorticity is twice the rotation rate. So you can substitute, if you remember what this, with the same example, what d beta and d alpha is. Using the same example as before. Just using the same definitions of alpha and beta that we used before. This is, so you get rid of dt, you get rid of dx2 and dx1, and you are left with okay. So this is the vorticity around axis 3. Okay, so we just take the rotation, which is given by the rate of change of these two angles, which is 1, so the average of these two components. By definition, the vorticity is twice the rotation rate. Okay, so this 1 over 2 disappears. So you substitute your beta and alpha with the definitions that we gave before in that simple case. So the rate of change is, so you put the d by dt outside, substitute, and you end up with this. Okay, so this is the vorticity, the third component of the vorticity, because it's in the third axis. And now you can generalize as this. Okay, if you generalize the three component, the vorticity vector will be equal to the curl of the velocity vector. Okay, because this, you know, if you do curl. Okay? So the vorticity is the curl of the velocity vector. And you can write this in tensor notation using the alternating tensor. And you can write the vorticity of the fluid in tensor notation using the alternating tensor. Okay? So if you want to look for what is usually the case, the vorticity in the third component in x3, you just do for I equal 3, all the jk, you will see the alternating tensor. In some cases it will be 0, some other cases it will be -1 and +1, and you will end up with this for omega 3. Okay? So for I equal 3, you will end up with this. Okay? So you can write the vorticity of the element as the alternating tensor of that. Okay, so that's why the shear strain rates are important. So an element of fluid can be subject to linear strain rates and deform linearly, or be subject to a shear, okay, and deform because of the shear. That particular shear might provide vorticity to the fluid element. So if you have a simple element like this, there is a shear in this direction, and the fluid particle will start to rotate. Okay? If it starts to rotate, it has acquired vorticity. Okay? And the vorticity is given by the curl of the velocity vector. Vorticity might be 0. So if these two are equal, then vorticity is 0, of course. Okay? And it's just deforming, but it's not acquiring any vorticity. An ideal fluid, for example, has vorticity equal 0. And here's the graph. Okay, so I'll send you all this. This is a better drawing than mine. Okay, so subject to a shear, subject to a shear strain, you might have a shear strain rate, and that shear strain rate might provide a vorticity to the element of fluid. Okay? And you can describe the linear and the shear strains through that strain rate tensor, okay, which has all the 9 components. The diagonal are the linear strain rates, and the off diagonal are half of the shear strain. Okay, so just 3 things: linear shears, linear strain rates, shear strain rates, and vorticity, which is provided by the shear strain rates. Okay. And if you do seismology and solid earth, then you're going to be playing with linear strain rates and shear strain rates all year. No questions? Now we're late for the